Hi, my name is Han.
So you won the honorable prize, right?
Best student paperwork.
Best student paper.
Yeah.
Student, perfect.
Student paperwork, yeah.
Okay, so let me just welcome people back.
Sure.
Hello. Welcome back. This is the Analyzing Humans in Images session. And just a couple of reminders while you settle down. Remember, there are a couple of microphones on the halls for you to ask questions, and we'll be taking your questions after the talks. And also, if you are presenting a spotlight, please come to the front. There's a seat for you here. So we'll start with the first talk by I'm also co-chairing this session with Alex Alahi from EPFL. My name is Juan Carlos Niebles from Stanford. So the first talk is by Hanbyul from CMU, and he also won the Best Student Paper Award, so we look forward to your talk.
Thank you for the introduction, and good afternoon, everyone. Okay. We humans communicate tremendous amount of information with very subtle body motions. Notably, these social signals are usually transmitted by the organized motion of the whole body with facial expressions, hand gestures, and body postures. However, no previous method can miraculously capture all these details at the same time. So the goal of our work is to build a deformation model which can express the full spectrum of human body motions, including faces, bodies, and hands. Our model is parameterized by a shape parameter phi, and a motion parameter theta, and a global translation parameter t. And note that our model can capture the shape and pose of all body parts, which we call the total body motion capture. There has been groundbreaking work in capturing and modeling human bodies. However, each area has its own preferred capture configuration. For example, facial motion is captured at close range, assuming little global head motion. Body motions are captured in a sufficiently large working volume where people can freely move. Hand motion is captured at very close distances from the hands. These are often considered as separate problems, except the recent work of Romero et al., and these separate configurations make it difficult to perform the total body motion capture. As an example, let's take a look at this video where three people are communicating. Look at the way they are using their fingers and their facial expressions. As can be seen here, a lot of human social signals are expressed by the combination of all body parts. If only body motions are captured, for example, by using a model which can express only the torso and limb motion, all important signals from the hands and faces are missing. Using our method, we can measure the 3D motion of entire body part, including faces and fingers. Note that this result is reconstructed by frame-by-frame processing without using any temporal information. As you can see, capturing all parts together makes the human motion more realistic. But directly building this model from the scratch is challenging because it requires accurate reconstruction result with detailed faces and hands. Here, multi-view stereo reconstruction result are shown, and it is hard to capture all parts at high resolution due to the differences of their scales. The key idea of our method is to leverage the existing generative models for each part. Our final model is defined by stitching the following three part models: body part model, face part model, and hand part models in a single skeleton hierarchy. For the face model, we use the popular face warehouse model, and in this framework, a 3D face mesh can be represented by the summation of the mean shape and linear combination of the shape component, and a linear combination of the motion component, which represent facial expressions. For the body model, we use the popular simple model with some modifications. In this framework, a 3D body shape can be represented by the summation of the mean shape and linear combination of shape variation component. And the body pose is controlled by pose parameter theta, which controls the underlying skeleton. Body shape and the skeleton are related by the standard linear blending skinning. Note that here, we don't use the pose-dependent shape variation component of the original simple model to simplify our optimization process. For the hand, there was no available generative model at the moment, so we made a homebrewed model. So to enable the shape variation, we performed naive scaling for each bone. And the pose is controlled by the angle parameter for each joint. Finally, we stitch these part models together as follows. First, given the body part model, we remove rigid part on the faces and hands. Then we stitch the face model to the body skeleton hierarchy. Here, we use the transformation to align them, which is fixed across time. Similarly, we stitch the right and left hand models on the body skeleton with additional transformation for the alignment. At the end, we apply a blending function to generate a seamless mesh structure, which we call this model as Frank model. Our Frank model can be fitted by minimizing a cost function. And the first term is to match 3D key point measurement. To obtain that, we use the open pose detector, which provides 2D key point for face, body, and hands. And this is example views on a calibrated multi-view system. However, a very important part, body part, the foot is missing here, and there is no available foot detector. So in this work, we built a new foot key point detector using convolutional neural network by collecting manual annotations. Please see our paper for details. Then the 3D key point of entire body part are reconstructed by triangulating them. Our 3D key point measurement contains face, body, fingers, and feet. And for the second term, we minimize the distance between our model to the 3D point cloud measurement using ICP. And this is to capture the shape of the target person. The 3D point cloud is generated by a multi-view stereo algorithm, and this term is optional in our framework. The third term is required to avoid artifact among different parts. More concretely, Frank model keeps the separate parameterization for each part, thus shapes are not necessarily aligned. To avoid this, the sim cost function minimizes the distance between parts, which are shown as green lines here. And as the final term, we use a Gaussian like prior for shape and pose parameters. And this is an example result by using our Frank model. In this example, only 3D key points are used for the fitting without using ICP term, and the reconstruction is performed frame by frame independently. Facial motions are also captured by the same model. Although our Frank model can be directly used for total motion capture, it has limitations. First, it has a complicated parameterization from separate part, and also it requires the sim cost function to avoid artifact. And the shape space can only cover bald head and unclosed body due to the nature of the part models. To overcome these limitations, we present another new model, ADAM. To build ADAM, we fit our Frank model on many samples with diverse shapes and poses. The Frank model makes it possible to reconstruct details, face, hand, and body shapes in the same mesh topology. And we deform the fitted Frank model to get additional details such as hairs and clothing. To this end, we learn the shape variation space for the entire part by using PCA. And this is the final ADAM model parameterization. The shape of ADAM model is defined by the sum of the mean shape and linear combination of the shape variation component. Here, this shape variation component controls body, face, and hands together. And we keep the facial expression component of the original face warehouse model, which is already compatible to our ADAM model's face part by construction. And the pose parameter controls skeletons, including body and fingers. And here we also use standard linear blended skinning function. For the experiment, we use the data captured by the CMU Panoptic Studio. So here we use 120 visual cameras for the body key point measurement, and about 30 high-resolution cameras for faces and fingers. And this result shows a juggling motion. So using our method, we can capture the interesting hand motion of this juggling sequence. Our motion capture output is the same as the usual motion capture system. So our result can be directly used for graphics applications, such as character animation here. This sequence shows more common body motions, such as keyboard typing. Again, all the results are reconstructed frame by frame independently. And here the model with silver color is the Frank model. And the gold color shows the Adam model. Adam has much simpler parameterization. In this sequence, my advisor, Yaser, is playing a piano. I think sound is not. Okay. Note that our cameras are located in a pretty far distance from the fingers, but still they are accurately reconstructed. And in this sequence, hand motions for diverse tools are captured. Here, we only use 3D key point measurement for the fitting. And again, frame by frame processing. In summary, we present a stitched Frank model for total body motion capture. And Frank allows us to build Adam, which has much simpler parameterization. Especially, our tracking heavily relies on 3D key point measurement, and we demonstrate that this measurement enables a robust motion capture result, even in frame-by-frame reconstruction. As a final note, we are releasing the data set captured from our Panoptic Studio system, including the point cloud from 10 Kinect, and 3D key point measurement for face, body, and hands with corresponding videos at 40 different viewpoints. We also plan to release the new OpenPose version with fit key point detector. Thank you for your attention, and I'm very happy to take any questions.
Thank you, Han, for the interesting talk. We have time for a couple of questions. Okay, I do have one question. So it seems like the prior component you have in your model is helpful to sort of constrain the space of poses. And I wonder if it becomes too restrictive to the point that it's difficult to handle with new body pose configurations. So have you studied this effect?
So maybe, are you talking about the final, the last prior term we are using? That is only, the prior term we are using is actually very simple, and we are using really minimum weight for the term. That is only for stabilizing the optimization, and actually it has a really minimum effect. Yeah.
I see, but do you have any way of studying whether your model performs well in unseen poses?
So actually there is no big constraint for the pose. So in some cases, it's actually unstable, especially since our target is mainly, so the measurement we are using is mainly the joint location, meaning the twist kind of direction is unstable, because there is no way to determine that. Even by using the ICP cannot overcome this one. So to avoid that, probably we need to use some post-prior, which is somehow explaining the feasible motion space, but that is currently missing.
Yeah. So you have,
Yes.
So I have a quick question. I don't really understand what's the input for this system. Is it include only single images, or you need to have all the Kinect and camera input? Another question is, what kind of optimization did you use for the energy minimization, and what is the computation power for this algorithm?
So for the first question, in our case, so the model is just fitted to the measurement we can get. So the measurement can be obtained from any system. So here we are using this big system because we already have, but you can use actually a smaller system. For example, in our lab, we recently built much smaller system with just 4 cameras, which can still produce 3D key point by just using triangulation. But still, model can be applicable for that. And as an interesting future direction, probably we can apply the same model for single view. That is our current work. For the second cluster, we just use simple gradient descent algorithm by using Ceres library from Google.
Okay, thank you very much.
All right, let's take the next speaker for the amazing talk.
Thank you.
HTML. It's a great pleasure to have Seungryul from Imperial College to present his work. Thank you for introduction and good afternoon, everyone. Today I will gonna introduce our work, Augmented Skeleton Space Transfer for Depth-Based Hand Pose Estimation. This work collaborated with Kwang Kim from University of Bath and Tae-Kyun Kim from Imperial College. Also with thanks to our sponsors. Hands are primary interacting interface in a daily activity, and detecting their pose and gesture is important for virtual reality and augmented reality applications. And we can find other important applications like sign language recognition and robotic grasping, where the hand poses are important. And in 3D hand pose estimation, given a depth image, we try to find skeletal representation. And to do that, we run a hand pose estimator. The main challenge of hand pose estimation is that their hand pose space is huge. The main variations of hand poses are the viewpoint caused by the different camera perspective and the shape variations depending on different humans, and the articulation variations depending on different configurations of fingers. So collecting database covering all these combinations is not easy. Also, self-occlusions makes the depth map change a lot, even with slight hand pose variations. So we need to fill in the space densely. So there's some efforts to collect real and synthetic data to cover this huge space. The issue in collecting the real data was the annotation method. In previous ICPL, NIU, and MSR dataset, they use tracking and refinement method. And in last CVPR, the use of physical sensors and inverse kinematics were proposed to automatically and accurately annotate the hand poses. And they collect 2.2 million database to cover a huge hand pose space, but still their data is lacking in combination of three variations. And there has been the approaches using the synthetic data, but synthetic and real data has a discrepancy. And in last CVPR, reducing the gap between synthetic and real data has been proposed, but we observed that there was no interaction between data generator and hand pose estimator. In different perspective, to deal with the viewpoint variations, some use intermediate 3D representations, but basically their approach is limited in that it is not for full 3D reconstruction, and self-occluded pixels are remained as self-occluded. So I will introduce our approach. Before that, I will introduce the difficulty of editing depth space. So from the leftmost original depth map, I rotated the point clouds, but rotating the 2.5D depth map in 3D results in many missing pixels. And even changing the hand shapes is more non-trivial. Instead, we first augment the skeleton space with unseen shapes and viewpoint from the pair data. The pair data is obtained from the conventional data set, and from their skeletons Y, we rotate the skeletons by sector 1 or sector 2 according to the Y-axis and x-axis. And the tau means the ratio bone length increment. So for the shape variation, we change their bone length. And we sample those 3 parameters from the normal distributions, and we augment the skeleton space 10 times from the conventional data set. So the rightmost is the TSNE plus for our augmented skeleton space. Blue points shows our augmented skeleton space, and the red points shows the skeleton space from the big hand data, and other colors denotes the samples from the other conventional data sets. Then we perform the joint training of hand pose estimator and hand pose generator. The purpose of joint training is to generate the corresponding depth map for the augmented skeletons and simultaneously train HP hand pose estimator with both paired and unpaired data. To perform the joint training, we have 4 kinds of networks. The first is the hand pose estimator, which estimates the skeletons from the depth map. And the second is the hand pose generator that synthesizes depth map from the skeletons. And we have 2 kinds of discriminators. One is for depth, and the other one is for skeletons. And they discriminate fake and real samples. The hand pose estimator and the hand pose generator can be trained by using paired data, depth map, and skeletons by minimizing their L2 losses between network predictions and the ground truth. To make the result more realistic, we add the adversarial loss here. And then we enforce the cyclic consistency to interact between HPE and HPG. So the output of when the output of HPE is fed to the HPG, the synthesized depth should be similar to the original depth. And when the HPG output is fed to the HPE, the resultant skeletons should be similar to original skeletons. Also, we enforce the cyclic consistency on the augmented skeletons. And because the augmented skeletons have no corresponding depth map, we enforce the cyclic consistency on the synthesized depths. So this is our whole pipeline for the joint training. The red path is used by the paired data, and the green passes are used by the unpaired data, and the blue passes are used by both paired and unpaired data. And the objective of joint training is to train HPE with both paired and unpaired data. And the HPG and discriminator also sees more diverse samples. So our whole losses are a combination of 4. The first LG is the L2 plus adversarial loss for the HPG. And the LE is similar to previous one for HPE. And LP is the cyclic consistency loss for the paired data, and LU is the cyclic consistency loss for the unpaired data. So this slide shows some intermediate result for transfer depth map. The first line is the synthesized HPG output, and the second row is the nearest samples in training DB. So we can see that the HPG can generate different shapes from the training DB. And this is for the viewpoint change. And the left column shows the elevation change, and the right column shows the azimuth change. So we can also observe that diverse viewpoints can be generated. And this is our inference method. So given a depth map, we infer the initial skeletons by feeding the depth map to the HPE. And then we further refine the once estimated skeletons by using gradients from the HPG and the skeleton discriminator. We further propose multi-view ensembled refinement. For the so we rotate the estimated skeletons multiple times and receive gradients for each multi-viewed skeletons from the skeleton discriminator. And we average them to output the final result with the updates from the HPG. So this is our result on the loss configurations. The red fonts shows the HPE and HPG result induced by the paired data using LE and LG only. And the blue fonts shows the HPE and HPG induced by the paired data using one more cyclic consistency loss for the paired data. And green shows the HPE and HPG result induced by both paired and unpaired data using the full supervision. And the black color shows the HPE result with the testing refinement. So we can conclude that HPE and HPG improve their accuracies as more supervision is used. Also, this is our main experiment on the hand pose estimation. We use 4 hand pose data sets. The first one is big hand 2.2 million, and the second one is ICVL, and the third one is the MSRA, and the last one is NYU dataset. In 4 datasets, we observed that our method consistently improves the baseline approach and on par with the state of the art. And interestingly, we trained the HPE using big hand plus our method and test on each dataset for MSRA and ICBL. And interestingly, for the MSRA dataset, the transfer running achieves the state of the art. So this is our demo, and the left is the hand pose estimator without augmentation method, and the right is the our method. So we can observe that for different viewpoints, our result is more stable than the left one. And this is the summary of our work. We first augment the skeleton space, and then we do joint training of HP and HPG, and observe that the results are improved as more supervision is used, and we obtain the state-of-the-art result. And this is the end of my presentation, and you can come to poster number A4.
Thank you very much. Any questions in the room? No questions? We are looking for the next speaker also. He's here? Awesome. Can you share about the computational complexity?
As you can see, the testing is almost real time using the. As you can see, the testing is almost real time using the GPUs.
So you on the GPU?
Yes.
Thank you.
Thank you.
So the next talk is from Guha from MIT. Thank you.
Thanks. All right, thank you. Today I'll show you how we can imagine the unseen with images of humans. So take a look at this image of a professional golfer in the middle of a swing. Now, could you imagine what he may have looked like if, instead of deciding to golf that day, decided to do some yoga on the golf course? You could probably imagine that, right? Even though you've likely never seen him or any other golfer doing that before. In this work, we propose an automated method that takes an image like this and produces a new image like this, showing what the person would look like in a different desired pose. In this case, the pose of someone doing yoga. So the problem is as follows. Given an image of a person that we call the source image, along with the 2D pose of the person that we call the source pose, and a desired 2D pose, the target pose, the output is ideally a realistic image of a person in that target pose with the same background. The task is complicated. First, pose transformations can cause complex image changes with several different moving body parts and self-occlusions. In addition, occluded parts of the background need to get filled in if they become disoccluded in the new image. So we propose a learning-based model for this, implemented with a neural network, that we train in a supervised manner with a reconstruction loss function that makes sure that the synthesized image agrees with a ground truth image label. Now, the first thing you may think about trying is something common with other image synthesis works, such as a UNet style architecture. And indeed, we did try this at first, where we pass in the source image along with the source and target poses, here represented as images, through this UNet, which learns some complex relationship between the pixels of the inputs, and spits out some output image like this. As you can see from this image, we found that it resulted in a lot of bad things happening. For example, this instructor now has a green shirt when she didn't initially, and we also see artifacts in the background. So to address these problems, we design our network in a more modular way, splitting the problem into smaller, easier subtasks. This design is more intuitive than something like a UNet, resulting in a more interpretable network for analysis and debugging. And as we'll see later, it also produces better results. Our network has 4 modules trained together jointly, and importantly, we don't require any intermediate supervision for any of these modules. Remember that the only supervision we add is for the final output image. In short, our network takes the source image, segments them into different parts, moves the foreground body parts to new locations, and then synthesizes the foreground and background and merges them. And again, these 4 modules are trained jointly as one network. Here's the network diagram. For further details on the specifics, please visit our poster. It's poster A6. So the first module in this network does segmentation of the source image. The source image is passed through a convolutional architecture, which then outputs masks for the foreground as well as the different body parts. So here's an example of the outputs for 2 different examples. Each row is a different example. We see here that these are what the segmentation masks look like after training, and we see that they're quite precise to the different body parts. And keep in mind, again, that we don't have ground truth segmentations to train this. The network learns to do this from the input and output images of the training set. Given the segmentation of the different parts, we can now move them separately from one another. So module B moves the foreground body parts to new locations. It uses the source and target poses to compute a rigid transform for each body part and then moves it to the new location using spatial transform functions. So we see here at the top is an example of, this is for the golf example, we see the arm on top and the head on bottom. We see how the arm is moved, rotated quite dramatically from input to output using one transform, and the head is rotated slightly. Finally, once these parts are moved to the appropriate locations, module C synthesizes the foreground by merging and refining these moved parts together into one coherent foreground image with another convolutional architecture. And finally, module D synthesizes the background by performing image in-painting, where the source image has the target, so has the foreground removed, and it fills it in with appropriate appearance. And finally, the new background and foreground are merged together to produce the output image. So here's some examples. On the left is the source image. In the middle 3 columns, we see outputs of the background and foreground synthesis stages, as well as the output mask that tells where the foreground is. This is learned as part of the foreground synthesis stage. And finally, these 3 are matted together to produce the output image on the right with alpha blending. Notice that in the background image, how the synthesis stage is able to fill in the appearance behind the person effectively. For example, the lines on the court, the tennis court, and the fence, and the colors are realistic. And here's just some more examples for other cases showing that we can apply this to various scenes. The final detail I'd like to describe is the loss function, the reconstruction function. And what we found is consistent with previous literature in that L1 pixel-wise loss results in blurry images. A feature loss such as using a pre-trained VGG network on ImageNet gives you some more details, and to the surprise of no one, adding an adversary improves that further. And the results we show in this presentation are all using that final loss, the feature loss plus the adversary. And our code is available on GitHub at this address, so please take a look after this session. Okay, so now I'll describe the experiments. We evaluated our work on a data set of human actions and poses. We collected these videos. It was 266 videos downloaded from YouTube of 3 different action classes: golf, tennis, and yoga fitness. So here's some frames on the right-hand side showing just examples of the types of videos we worked with. As you can see, there's a lot of different foreground appearances and background appearances, indoors and outdoors, a lot of different textures and lighting, and so this is quite a challenging data set. We held out entire videos for the test set such that no person appears across training and testing, and we obtained poses by running a 2D pose estimator on all the frames for all the videos. And finally, we trained our model on pairs of frames taken from a single video. So that means the background is the same, the person's appearance is the same, but they're changing poses. So here's some results. On the left is the source image. The next image is the ground truth target image that we'd like to, ideally, we'd like to get that image. The UNet, as I showed earlier, produces something like this with that same target pose. Again, the appearance is off and the background's bad. And this is our output. As you can see, the person's appearance is retained as well as the background being quite clean. And here's some more outputs. The second row shows a tennis player. The UNet has successfully converted her to a more masculine player, as you can see, whereas we're able to keep the appearance. And notice also subtle details like the shadows or the shading on the lower legs, the calves, are accurate with the target image. And the final example shows that our foregrounds are just much better. So let me remind you that our model was trained on frames within the same video. But we're also, I think, able to do something very exciting, which is take a source image from one video and take a pose from a different video, even a different action class, and synthesize a realistic output. So here's a tennis player or tennis coach, and we took a golf pose, and we can synthesize something that looks reasonable. And we can do that for all different combinations of the action classes, tennis to yoga, golf to tennis, etc. Note that this is very challenging because we have to get the details, the clothing, the self-occlusions correctly, and yet it's able to generalize to that. And I'd like to leave you with a really exciting result, which is synthesizing video sequences. So given an image along with a sequence of target poses, we can synthesize a coherent video recording. So by that I mean we take a source image, such as this golfer image on the left, and a sequence of target poses, and apply our method independently to each frame. So we would take the first target pose, apply it to the first image, and do that for each. Notice that there's no temporal information that our algorithm has. And this is what the output looks like. On the left is the true video. On the right is a synthesized video, and we want these two to look alike because we took target poses from the true video. So there are several observations to make. First, the movement is pretty smooth, even though it has no temporal information, and this can be attributed to how our network explicitly accounts for movements. Notice textures on the pants, like the creases, are accurate for the different poses. And also the background is held quite consistent over time, and this can be attributed to how we decouple the background and foreground synthesis tasks. Again, this is exciting because the network could only see one image, the source image, and yet it was able to construct all these different views of the same person. So in summary, we proposed this modular architecture that was able to produce realistic synthesis of humans in different poses. We showed that we can synthesize video sequences, and again, the code is available. And please visit us today at the poster session. It's A6. Thank you.
Thank you, Guha, for the talk. Any questions from the audience? There's one question coming.
In the video, at the very end, you can see the bottom of the shoe. How did the model learn that the bottom of the shoe has a different color?
I can't hear you. I'm sorry.
In the video, towards the end, you can see the bottom of the shoe, and it has a different color. How did the model learn that the bottom of the shoe would have a different color without ever seeing that?
Near the end of the video?
Yes.
Well, it's seen enough golf pairs in the training set that it probably learned that most of them have a kind of dark, or there's a shadowing effect underneath.
Okay.
Does that make sense?
Yeah, in the same video, the golfer looks blurred. First, I mean, it's a really great work. But the golfer looks blurred compared to the original. Any reason why this is happening?
You're asking why is the golfer more blurred
Yes.
than the original? Yeah, I mean, I think in general, we find that some of the details are lost from source to target, and I think part of the issue is the loss function, I think.
Is it maybe alpha blending? You said that you were doing alpha blending, if I remember correctly.
Sorry?
You said that you were doing blending from the two scenes, the foreground and background. Is it possible that that contributes to the blurred golfer?
You're asking, is the separation of foreground background contributing
Yes,
to...
and blending that I understand.
No, I mean, I think the same issue is probably the same for both the foreground and background separately, because they're both decoupled from one another. And so I think you will notice some blurring in the background as well. That's, I think the same issue causes both.
Okay, thank you.
Yep. Sure, thank you.
Okay, that's all the time we have for questions. Let's thank our speaker again. That concludes the oral talks for our session, and now we move to the spotlights.
And it's 0-1 for Croatia, in case someone's... Spot like 6 and 12. If you're in the room, can you come in front? So, should you click on something? Should they click on something, or they just talk?
Good afternoon, everyone. I'm Junyo from Nanyang Technological University. I will present our work, SSNet Scale Selection Network for Online 3D Action Prediction. The task of online action prediction is to predict the class label of the ongoing action by using the observed part so far. There are several requirements of action prediction. First, the method should be fast enough for online applications. Second, we need to recognize the action at the early stages. And the third is there are multiple sequential actions in the untreated sequence. Sliding window over the temporal axis can be used for this task. However, there are two main challenges. First, it's very difficult to select the proper scale of the sliding window due to the significant scale variations at different time steps. For example, at the early stage of an action, we'd better use a small scale, while at the later stages, we need to use a large scale. That means the scale cannot be fixed at all steps. A second challenge is that there are redundant computations due to the overlapping design of the sliding window, and so the speed can be limited. To deal with the challenges, we propose a scale selection network. We use temporal 1D temporal convolution in the temporal dimension to model the dynamics in the all different frames, and the input of this network is the video frames. To deal with the scale variations, we use dilated convolution design such that different convolution layers in this network have different perception window scales. For example, the first layer, the scale is 2, while the second layer, the perception scale is 4, and the third layer is 8. Different layers have different perception window scales. We need to regress the proper scale at each time step. We aggregate the convolution actuations at all layers, and then use the fully connected layers to produce a estimation of the proper scale, and this scale indicates the distance to the start point of the current action. Since we have get the proper scale at different steps, we then need to, we can use it to determine the proper layer in the network. And this layer covers the preferred part of the ongoing action. Since the action prediction is based on the proper window scale at different time steps, our method can produce a reliable result. To deal with the overlapping computations, we also propose an equation sharing scheme such that the overlapping redundant computations in the sliding base design can be avoided. And in this design, the features computed in the previous time steps can be reused by the later steps. We perform experiments on 2 data sets. Our method obtains the state-of-the-art performance. Specifically, our method outperforms the fixed-scale network and also the LSTM-based methods. Moreover, our method achieves close result to the network by using the ground truth scale for action prediction. Thank you.
Okay, hi everybody. I'm Georgia. I'm from Facebook AI Research, and today I'll be presenting our work on detecting and recognizing human-object interactions. And this is in collaboration with my colleagues Ross, Piotr, and Kai-Ming. So undoubtedly, visual recognition has seen great progress over the recent years. But as machines get better at detecting and localizing objects and images, they tend to dismiss the fact that objects exist for a purpose. And this purpose usually manifests itself through interactions with objects, with humans, or even the scene itself. So it's exactly these interactions that we study in our work, and in particular, we focus on human-object interactions. This is because humans interact with objects in the most interesting and diverse ways. So the task here involves localizing the human instance, localizing the object of interaction, and correctly predicting the interaction type. So before we dive into the details of our approach, I just want to discuss some useful insights regarding this problem. So first, let's note that a human instance can participate in many actions and can interact with many objects of interactions at the same time. The appearance of the instance is very revealing about the interaction type, but also about the relative location of the object of interaction, even if it's not visible. And of course, interaction recognition heavily relies on accurate object detection. So to tackle this problem, we propose an end-to-end system that recognizes all interactions in an image. We call our model InteractNet. InteractNet consists of 3 distinct parts. First, the object detection branch will detect all objects and all humans in an image. These detections are then going to be used from the subsequent parts of InteractNet. The second and most important part is the human-centric branch, which takes as input the human instance and predicts the interaction type, as well as the relative location of the object of interaction. We also show some output predictions of this branch. We show the detected human instance with a blue box, and also the prediction of the relative location of the object with a dashed yellow line. And as you can see, our model is able to guess correctly where the object is, even if it's not directly visible from the human bounding box. And finally, the interaction branch will take as input the appearance of the human object, as well as the appearance of the detected object, and will assign a score for each human action object triplet candidate. We benchmark our approach on the VCOCO dataset. On VCOCO, we applied all the different parts of InteractNet, and where we show that every component matters, and the biggest gains coming from the target localization branch. And all this at a very good speed of 8 frames per second. We also show a result in the more recent and more challenging HECO-DAT dataset, where we again show the superiority of InteractNet. For many, many, many results and more details of our approach, please come by our poster.
Hello everyone, I am Fadime and I'm a PhD student from the University of Bonn in Germany. Today I present the work I did with my supervisor Angela Zhao. The title is Unsupervised Learning and Segmentation of Complex Activities from Video. We define a complex activity as a procedural task with certain steps or sub-activities that follow a loose ordering. Here, in case of making coffee, we have these 6 sub-activities. Our aim is to discover and segment the steps of a complex activity from collections of videos. We assume we are given a collection of videos, all of the same complex activity, and we specify K, the total number of sub-activities. Our aim is to find and temporarily localize these sub-activities. What's making this task so difficult? First of all, in these complex activities, the ordering is loose but not fixed. There might be a lot of background or garbage frames which are not relevant to what we are interested in. There are huge appearance variations. For example, here you see some examples of the filling water subactivity. And sometimes these appearance variations also can be quite confusing. For example, here you see 2 different subactivities, put stow and remove stow, that have very fine grain differences. And in some complex activities, you might even skip some steps. The way we do unsupervised discovery and segmentation is to iteratively learn. Given some initial segmentation, we alternate between learning a discriminative appearance model via clustering and learning a temporal model for the activity. Then we construct a new segmentation and we iterate, repeat this process. We use a redundant form of representation where we split the actual segmentation into a bag of subactivity labels A, and an ordering pi. If you put everything together, this is the joint diagram of our overall model. Given some segmentation, we can define an appearance model. The segmentation is composed of the bag of subactivity labels, which we model as a multinomial, as well as the ordering pi, which is based on the Melos model. The more novel aspect of our model is the way we handle this temporal modeling. We treat the ordering as a sequence of permutable subactivities. In this way, we can model a distribution over permutations. In particular, we use a Melos model. The Melos model is defined as follows. Given a canonical ordering sigma, and given an observed ordering pi, we can define the likelihood of this ordering as an exponential function based on the distance between the canonical ordering and the observed ordering, and some dispersion parameter rho that controls how much the distance influences the likelihood. The advantage of using a Melos model is that it allows for enforcing global ordering constraints. It also allows for missing steps and deviations, and it's compact. Parameters grow linearly with the number of subactivities. We tested our method on the breakfast actions dataset and the INRIA instructional videos dataset. In both datasets, we are either comparable or we outperform the state of the art, even though our method is fully unsupervised. Thanks.
Hello, I'm Kyle Genova, and today I'm presenting unsupervised training with 3D morphable model regression. This project was a collaboration between Princeton University and Google. Our project's goal is to reconstruct the 3D geometry of a person's face from only a single low-quality input photograph. Being able to robustly estimate facial geometry has a variety of applications. We would like to specifically target virtual avatar generation for video games and VR. In this application, the reconstruction must isolate the identity of the subject so that pre-created animations can be applied to it. Because the inputs to this task come from end users, we would like to tackle hard input cases like those shown here. This includes significant occlusion, out-of-plane rotation, and unknown lighting. We must also strip away arbitrary input expressions. What we want is a recognizable and animatable morphable model for each of these photographs. We believe the most important attribute of our reconstruction is the recognizability of the identity. How much does a user believe that our output geometry looks like the person in the input photograph? Humans are good at this kind of identity discrimination, and now CNNs can do it as well. Neural networks typically recognize faces by projecting images to a low-dimensional feature space where embeddings are nearby for images of the same person and are far away otherwise. Previous work has shown that these embeddings consider all parts of the input face, leading us to use a face recognition network's embedding distance as a proxy for human judgment of geometric similarity. We therefore train a network to output 3D face geometry from a single photograph and use the following novel loss function. When the output geometry from our network is re-rendered with random pose and lighting parameters, and that re-rendering is run through a face recognition network, our geometry's embedding should be nearby the embedding of the original input photograph. In our training scheme, input photographs are first passed through a face recognition network. So our trained network, the yellow box, takes as input a face identity vector. The output of our network is a 3D morphable model. We assume no supervision other than a data set of completely unlabeled faces, access to a pre-trained face recognition network, and a morphable model of faces. We use Google's FaceNet for both identity encoder steps. In order to train our geometry prediction network, we require backpropping through a rasterization stage. We create a new differentiable renderer that is integrated directly into TensorFlow. This renderer is now publicly available. Because our loss comes from a fixed, pre-trained network, and because our 3D morphable model output is fairly high dimensional, we require additional losses to avoid overfitting and network fooling. You can learn more about these losses in our paper. To evaluate our system, first I want to show you results on some of the examples that I highlighted earlier. Let's focus on a few examples in more detail. Here we see we can regress good identity parameters even for these hard cases. The recognizability of our results is state-of-the-art. Here is one subject under a variety of extreme pose, expression, lighting, and occlusion changes. We can even reconstruct reasonable likenesses from some artistic depictions. Thank you for listening. Please come to our poster session for a live demo. We can run our algorithm on your photo and have a webcam ready. You can even make a silly face if you'd like.
Hello everyone, my name is Timo Aldig and I'm presenting our work, Video-Based Reconstruction of 3D People Models. The work is joint work with Markus Magner from Technical University of Braunschweig and Waipeng Siu, Christian Theobald and Gerard Ponsmall from the Max Planck Institute for Informatics. In this work, we introduce a novel method for estimating accurate 3D body models of humans from a single monocular video only. The input sequence is shown on the left and our result is shown on the right. Notice that we capture accurate body shape, clothes, and hair despite having only a monocular video as input. The demand for accurate personalized 3D avatars is growing. Applications like tracking, body measurement for fashion or health, and virtual and augmented reality applications can benefit from personalized body models. Especially for VR applications, it is very important that the users feel well represented by their avatars. However, so far monocular methods have been limited to estimating parameters of a parametric body model. The results as shown here are not closed and do not really resemble the subjects in the images. Methods going beyond that rely on depth data or expensive scanning equipment. Instead, we recover the full body, including hair and clothing, as a free-form vertex problem. Our method relies on silhouettes, similar to the well-established visual hull-based 3D reconstruction. However, in our case, the subjects move between two views. This means, for every silhouette that we're looking at, a new pose enters the optimization problem. In order to now reduce the complexity of the problem, we perform the following trick. First, we compute an initial body shape and a pose for every frame by fitting the simple body model to 2D joint detections. Next, in order to add details, we associate first every point on the silhouette with a vertex on the surface. Then we apply the inverse pose deformation on the silhouette projection rays. We call this procedure unposing. The unposed rays from all frames form now a visual hull independent of pose. We now can effectively optimize body shape parameters and freeform vertex displacements to explain all silhouettes. Our objective function minimizes the distance between silhouette projection rays and vertices of the body model in T-pose space. Finally, we compute a median texture based on the input views. We evaluated our method on one real-world and two synthetic data sets. In total, we captured body shapes for 28 sequences. Our method was able to reconstruct the body shapes within a reconstruction accuracy of 4.5 millimeters. Additionally, we recorded our own data set consisting of 24 sequences for qualitative evaluation. Results are shown here. Our final avatars can be easily animated and also reshaped. Our dataset and the source code for our method are available for research purposes under the given URL. If you're interested in our work, you're welcome to visit us as poster B5 for details, questions, and more discussions. Thank you.
The next one.
Hello, my name is Yibo Hu. I will talk about post-guided photoelastic phase rotation. When we talk about rotation, there are three directions in 3D space: yaw, pitch, and roll. Phase rotation we mentioned here aims to rotate a normalized phase to arbitrary poses, where only yaw is considered. It has great application value, for example, as a way of data augmentation to learn from the generated data. As a result, phase rotation has received extensive attention from academia and industry. Phase rotation still faces many challenging problems. Taking the case of phase fractalization as an example, without any priori information, we are unable to know the unseen phases. So the process of fractalization is a one-to-many ill-posed problem, which is the main reasons why some previous methods have unrealistic, low resolution, and poor identity preserving results. Here we list a sample timeline of deep learning-based phase rotation since 2015. Phase rotation has gradually attracted more and more attention. CPF fractalized a profile to its corresponding frontal wave. Then DR-GAN tried to synthesize a frontal phase to the profiles. FF-GAN first tried to fractalize a phase in the wild. The next TP-GAN was a milestone in phase rotation, which synthesized photoelastic phases. In NIPS 2017, DA-GAN tried to literalize a phase in the wild, and now our method can not only fractalize a phase, but can also rotate a phase to an arbitrary pose, both in a controlled situation and in the wild. The contributions of this work are as follows. A couple-agent post-guided GAN is proposed for phase rotation from a single image in two-dimensional space. The landmark heat maps are used as a controllable signal in post-guided generator to synthesize phase images. Compared with the previous methods based on post-degree of 3D information, the heat map provides a flexible and efficient way for both learning and inferences. We propose a couple-agent discriminator to effectively combine domain knowledge of the post and topological structure to reinforce the realism of synthesized phases. Therefore, we have two conditional adversarial losses. In addition, we use a multi-scale pixel-wise loss, an identity-preserving loss, and a total variation realization. This slide shows the phase fractalization results on the multiplied data set and the small poses, where the red rectangle indicates our results, and the green rectangle shows the ground truth. There are some fractalization results and large poses. Our method can still preserve identity information to a certain extent. One of the most important applications of phase fractalization is recognition via generation to improve the accuracy of cross-wave phase recognition. Thus, we conduct quantitative experiments on the multiplied data sets, where we choose the light CNN as the baseline recognition model. By using our method to synthesize profiles into corresponding frontal faces and then recognize them, the accuracy of cross-wave face recognition can be greatly improved, especially under large poses. Here we take 0-degree frontal faces as input and use the landmark heat maps of different poses as the control conditions to synthesize the profiles. Further, we would like to generate a profile directly from another profile image. Here, for each group, the left column is the input and the right column is the synthesized results. In order to test the continuity and the generalization of our method and under the unseen poses in the training set, we interpolate facial landmarks and generate the following GIF images. What's more, we perform phase fractalization experiments on the LFW dataset. It's worth nothing that our method is trained on multiple dataset and directly tested on LFW. Okay, that's all. Thank you.
Okay. Hey, I'm Lak. So creating high-fidelity 3D digital double of person is really challenging. So you typically need to have a high-end capture system to do that. And right now I'm going to show you how we're going to do it using a deep neural network to achieve the production level 3D model. So a typical production pipeline, we use multi-view stereo to reconstruct the base mesh, which contain the general phase shape and expression. The high-frequency detail like fine wrinkles and samples are captured using photometric stereo, and which is not available for all of us. So we propose to use a deep neural network to learn the displacement map, which is a standard way to store the high-frequency detail for production. So inspired by the recent event in image-to-image translation, we want to use that network to translate the texture into displacement. But learning the high-frequency detail like skin pore and creases are very hard. So naively apply the translation network, we'll end up losing out the pore level detail you can see on the top row. So we propose to use two subnetworks to deal with the mid and high frequency separately, and we can get the result in the bottom row where skin pore at the skin feature at all scale are reserved. And the proposed network can generate 1K displacement map, and we want to upgrade it to 4K to resolve the mesoscopic detail. And we do this by using a patch-based super resolution network. The input displacement map is divided into small patches, and these patches are then fed into the super resolution network to get to the final 4K displacement map. To recap our pipeline, first we set up a passive capture to get the base mesh and the texture map. The texture map are then fed into the translation network to get the mid and high frequency displacement map. Then we upgrade this map into 4K to get the mesoscopic detail. And then we combine this 4K displacement and the base mesh to get the final mesh with sub-millimeter pore level details. And the set of our system comes from the quality of data set. Our data set contains 328 light state scans with sub-millimeter accuracies. The scan covers 19 subjects of a wide variety of ethnicity, ages, genders, skin tone, and expressions. And all the scans have a consistent topology and are very well corresponded. Next, we will show some results that will show that our model can generate high fidelity skin pore and fry wrinkle details. Okay. And also the model can learn to the difference in pore distribution in different regions of the face. To show the robustness of our model, we also applied it to the dynamic performance video. As you can see right here, the info detail is very consistent and contain no temporal noise at all. And we can also combine our model with the previous texture inference technique to generate mesoscopic detail for unconstrained image in the wild. And we also have more results and validation with many state-of-the-art methods. So if you are interested, we can come to our poster. I can explain more to you. Thank you.
Hello, everyone. My name is Liu Haoge. I'm going to present our work, HandPointNet, 3D hand pose estimation using point set. This is a joint work with Yujun Cai, Junwu Wang, and Professor Junsong Yuan. In this work, we consider the problem of 3D hand pose estimation from depth image. The input is a single depth image, and the output is the 3D hand joint locations. This technology can be used in virtual reality and augmented reality applications. Many of the recent 3D hand pose estimation methods are based on convolutional neural networks. However, 2D convolutional neural network taking 2D depth map as input cannot fully utilize 3D spatial information in the depth map for the 3D hand pose estimation. Some state-of-the-art methods include depth map as 3D volumes, use 3D neural network to infer 3D hand pose, but the time and space complexity increases cubically with respect to the input volume resolution, and the volume representation is unnecessarily voluminous. Since the depth map can be naturally converted to a set of 3D points, then can we estimate 3D hand pose directly from point cloud? Compared to 2D convolutional network, learning on point cloud can capture 3D structure of the hand and is robust to viewpoint variations. Compared with 3D convolutional network, direct learning on point cloud is computationally efficient. In our work, we propose to estimate 3D hand pose directly on 3D point sets with the help of PointNet method. PointNet is a recently proposed method for 3D deep learning which takes a set of points as input and is able to extract features of the point cloud. It has shown promising performance on 3D classification and segmentation tasks. In our work, we developed this network model for the high-dimensional nonlinear regression task. In order to make our method robust to viewpoint variations, we first normalized the sampled 3D points in an oriented bounding box, which is tightly fitted to the input points. As can be seen, the orientation of the normalized hand-point cloud are more consistent. Then the sampled and the normalized 3D points is fed into a hierarchical point net. The network is trained in an end-to-end manner to hierarchically extract point set features and holistically regress the 3D hand pose. We visualize the sensitivity of points to filters at different levels in a well-trained network. As can be seen, different filters exaggerate different parts of the hand and capture hand structures from local to global. At last, to further improve the accuracy of the fingertip, we design a fingertip refinement point net, which takes nearest neighboring points of the estimated fingertip location as input and outputs the refined 3D location of the fingertip from a basic point net. Experimental results on 3 public hand pose datasets have shown that our method is able to achieve superior performance for 3D hand pose estimation in real time. And our code has been released on the website. Thank you, and welcome to our poster B11 for more details.
Hi everyone, my name is Asha Nagrani and I will be presenting our work titled Seeing Voices and Hearing Faces on Cross-modal biometric matching. This work was done with Samuel Albany and Andrew Zisserman at VGG Oxford. So the goal of our work is to investigate the correlations between faces and voices of the same identity, and to motivate this goal, I'd like to ask you the following question. Can you recognize someone's face after only hearing their voice? So there should be an example now.
Because it's filled with holes. It's filled with holes about building 7.
So from this first example, it's quite obvious what the matching face is, and that's because gender is a cue that humans use to solve this task. What if we now considered 2 faces of the same gender?
The lines are crossed, and you would hope in a situation like this where you have,
So once again, this task is solvable, not only because it's James Bond, but also because age is another factor that affects how your face looks and the sound of your voice. What if we now remove gender, age, and nationality clues?
I'm not a cold weather girl at all.
Right.
I've lived in...
So you can see the task is a lot harder now.
I'm not a cold weather girl at all.
Right.
I've lived in...
From this example, you can also see that the voice that we source is always from a different video to the face. And the question that we want to investigate in our work is, can we train a network to solve this task automatically? And we show that yes, we can. And in fact, all the examples that you've seen so far are actually correctly labeled examples from our test set. I'll now describe the architecture that we use. So the input to our network is a triplet, which consists of 2 face images and 1 voice segment. And the goal of the work is to pick the matching face. We train a 3-stream CNN architecture, which consists of 2 face subnetworks and 1 voice subnetwork. The outputs of these subnetworks are then concatenated using a fusion layer, which allows the network to establish the correlation between face and voice. The entire network is then trained end-to-end using a binary cross-entropy loss on the selection of the matching face. So to implement the subnetworks, we actually use deep CNN architectures, and so we need a fairly large data set of human voices and faces to train the model. And hence we use the VoxCeleb dataset, which is a large-scale audio-visual dataset of human speech from YouTube. We train our model on more than 1,000 celebrity speakers and test on 189 disjoint speakers which are unseen and unheard by the network during train time. We then compare our results to a human baseline acquired using AMT, and we show that on random test pairs, our model manages to approach human performance, but on harder test pairs, after we remove variations in gender, age, and nationality, so for example, young female Americans, our model even manages to exceed human performance. We also consider a number of extensions in our work, such as using dynamic images instead of static images, and in this case, the manner of speaking becomes another important factor, which affects visual, facial motion, and the sound of the voice. We also extend this force matching task from 2 faces to n faces, and we also use visualizations in order to probe what exactly the network is using to solve the task. For further details, you can visit our website or come see our poster B13. Thank you.
Yeah, hi, my name is Shahroudy. I'm from CVPR from EPFL in Switzerland, and I present you a method for learning monocular 3D human pose estimation from multi-view images. So our goal is to reconstruct the articulated human pose shown on the right, given a single input image, here exemplified for skiing on the left. And obviously, we will do so with a neural network. You might think this is an easy task. We just train the neural network on a big data set, and we are done. However, existing data sets don't generalize very well to unconstrained scenes. So here, for skiing, we would have to create a new data set, capture a lot of images, annotate the 3D pose, and this is a very tedious, usually manual task. So to overcome this limitation, we propose a semi-supervised method to utilize unlabeled data, so less labeled data at training time. The idea is that we capture the subject from multiple views, and then we can use view consistency for self-supervision. So remember, at test time, we still want to be monocular. The network should operate on single images. But then at training time, we utilize that we have multiple views available. So let me exemplify this. We pick 2 views out of all the available ones, and then we apply our neural network F on each of them. This gives us 2 independent pose predictions. However, we live in the coordinate systems of the cameras. To ensure view consistency, we first have to normalize by the rotation of the cameras, and now we can apply a consistency loss. It's actually pretty simple. So it's just simply the least squares error between the 2 predictions after normalizing the poses. And this loss is enforced in a semi-supervised training setup. That means that we have a small label set, so pairs of images and 3D poses. We tell the network what 3D pose is and how to infer it from images. And then we utilize this additional set of unlabeled examples to make the network generalize to these cases not seen in the training set, not seen in the labeled training set. We have quite a few contributions. One of them is outlier rejection. Here the idea is we have multiple views. Some might be harder to predict than others. So we might have some self-occlusions. And we want to enforce consistency such that the hard view is learned from the easy one. Another contribution is that, well, for enforcing this view consistency, we need to know the view change from one image to the other. And to be fully self-supervised on these unlabeled examples, we propose a method to estimate rotation of the camera, so camera pose, alongside human pose. To evaluate our methods, we created a new data set. On the left, you can see the setup. It consists of 6 pan-tilt zoom cameras, like you have in a TV setup. On the right, you see examples with corresponding annotations. Because these cameras are rotating and zooming, we have to do 2 things. First, we calibrate them in each frame by clicking the small black calibration probes you can see. And then to get the 3D pose, we again click 2D joint locations and triangulate in 3D. If you work on multi-view geometry, this might be a nice test set. It's online. We use this test set to evaluate our method. We have 2 baselines. One is fully supervised, here in gray. Obviously, it has lowest error. And then we have the orange baseline. It's just trained on 1 subject out of the training set. We have 5 subjects, only 1 is used for training. The error increases. And then our method, it uses the same labeled amount of data as the orange one. And here in yellow, as you can see, we utilize the unlabeled examples. The errors decrease, sometimes being on par with the fully supervised baseline, sometimes even a little better. I will end this talk with qualitative results. Here you can see by using this self-supervision on unlabeled examples, we can improve pose reconstruction quite a bit. I couldn't go into all the details, so our method consists of quite a few components. Actually, without some of them, which I didn't explain yet, the post-prediction collapses. So if you want to know how it really works, please come to our poster B15.
Good afternoon, everyone. I'm Yaser Zhang from Shanghai Jiao Tong University. I'm happy to present the work Separating Style and Content for Generalized Style Transfer. As an interesting application of deep neural networks, image style transfer has drawn broad attention in recent years. However, most existing studies aim to explicitly learn the transformation from a certain source style to a given target style. Therefore, the learned model is not generalizable to new styles, and retraining is needed for transformations of new styles. Besides, many training examples are required for new style transfer. Therefore, we propose a generalized style transfer network. From the view of style and content separation, we represent each style and content with a small set of reference images and attempt to learn separate representations for styles and contents. And then, to generate an image of a given style and content combination is simply to mix the corresponding two representations. The detailed architecture is shown in the following figure. The whole framework is trained by trying to finish a series of tasks, generate the image with the target style and content, given a few of reference images. And by such a way, we expect the framework to learn to summarize from these similar tasks and learn to extract separate style and content representations, and then transfer this ability to new styles and contents. We here use the character typeface transfer as a special case to validate the proposed method. The dataset is partitioned into 4 subsets, which represent different levels of style transfer challenges. To validate the clear separation of style and content, we combine one content representation with style representations from 3 disjoint style references. As we can see, the generated images are similar, although the style references are different. It means that the style encoder extracts accurate style representations, since the only one thing the 3 style references share is the style. Similar results can be found for the content encoder. This is the results of our method for these 4 subsets. As we can see, D1 and D3 are generated better than D2 and D4. It means that characters with the known contents are generated better. Therefore, if we focus on the generalization of new styles, we can make all contents seen during training. This is the generation results for D2 subset. The baseline methods are trained using the same number of paired images as our model used for the target style. As observed, our method EMD performs much better than most baselines. This is the result for D4 subset. The baselines are trained using more than 300 paired images, but we only give our model EMD with only 10 reference images. Okay, thanks, and welcome to our poster at B17.
Hi, my name is Wenqi. Today I'm presenting Texture GAN controlling deep image synthesis with texture patches. In this work, we introduced the first deep image synthesis method, which allows users to control object textures. Users put one or more textures onto the sketch, and the network realistically applied this texture onto the objects. This problem is hard because the network has to propagate not just the color, but also the structure of the texture. And the network has to implicitly learn how to segment objects, understand 3D shapes, and synthesize texture, which are all difficult tasks. So, we start with the conditional generative adversarial networks with a combination of pixel, feature, and adversarial loss to ensure the result looks realistic. We extract input sketches and textures from real photos to serve as ground truth for initial training. But what if we want to generate texture that has never been seen on ground truth objects? In this case, we propose to add 2 local losses to further fine-tune our networks to handle diverse textures. The first one is local texture loss. We use the grand matrix of features from a VGG networks to represent the texture and minimize the cell loss to guide our networks. But cell loss alone is not enough. We observe that the network cannot produce low-level textures very well. There isn't much room for the network to be creative, since it tends to focus too much on structure and color. Therefore, we need a stronger constraint to ensure the high-level textures is preserved. That is why we introduced a new local texture loss by adding additional texture discriminator. This texture discriminator looks at a pair of inputs and addresses a fine-grained question: is this the same texture or not? Following such a discriminator is much harder and requires the generator to generate something that's not only realistic, but also faithful to various input types, especially to the user input types. We also conduct ablation study to verify the effectiveness of this texture loss. After applying this local texture loss, we find the network is able to apply texture more consistently across the object. Okay, let's look at more results. Users can put texture on anywhere on the sketch, and the network is able to texturize the object, while still keeping the result looks realistic. Because we trained this texture loss on a separate texture dataset, we're also able to handle various types of texture, even the unusual ones. In addition to just shoes and handbags, we also train on clothes. We train on deep fashion dataset. This is more challenging because image could contain different semantic regions, each with potentially different textures. In the future, we would like to apply a network on more complex scenes. So, we present texture again, which uses sketch to control texture, object structure, and uses texture patches to texturize the object. Our coded model available at textureagain.i.guttag.edu. Feel free to stop by and have a chat with us at posted location B19. Thank you very much.
Hello everyone, I'm Tribonish from MPI for Informatics. In this talk, I'll be presenting joint work with Mario Fritz and Bernd Schiele on performing visual reductions. People upload numerous images on the internet, thereby sharing delightful scenes, joyful events, and happy memories. However, a fact that is often overlooked is the human-centric information that accompanies many images. Upon closer inspection, we often find personally identifiable information such as faces, people, and fingerprints. Moreover, small details like license plates, timestamps, and names can be hidden in an image. In this work, we ask, how can we aid users by sanitizing images from a broad range of private content? We formulate the task as performing automatic reductions, where given an image, we want to remove private information by blacking them out. As an intermediate step, we identify privacy-sensitive pixels in images. Let us first look at this intermediate step. Previous works have predominantly looked into addressing privacy-sensitive classes in isolation. We extend such efforts by presenting the visual redactions dataset to simultaneously tackle a broad range of privacy-sensitive classes. We find that these classes, which we refer to as privacy attributes, occurs over multiple modalities, such as textual, visual, or multimodal. To this end, we present a large privacy segmentation data set covering a wide spectrum of privacy classes. To identify these attributes, we present methods which addresses privacy-sensitive regions occurring over multiple modalities in images. Some qualitative examples are demonstrated here. We achieve strong prediction performance across all attributes in this challenging task. Now we address our primary task of performing automatic redactions. Know that unlike segmentation, which requires pixel-perfect predictions, our call for redaction allows for leeway. We understand the influence of redacting fewer or more pixels in the image with respect to a scaling factor S. We now evaluate privacy and utility metrics and represent it in this plot. One can expect a trade-off between privacy and utility with higher privacy and lower utility with larger redactions. From a user study, we observe a nonlinear behavior in this trade-off. In particular, we find privacy is a step-like function. More importantly, different attributes and modalities allows different operating points for redactions. We evaluate our approaches over multiple such operating points within a privacy versus utility framework. The star symbol indicates the ideal region of high privacy and high utility of redacted images. As a baseline, we redact the human annotated ground truth segmentation at various dilations to obtain the green dashed curve. We then evaluate our redaction method at multiple thresholds to obtain the red solid curve. We find that pixel-perfect segmentation is a challenging task. However, by being able to calibrate our redactions, we already achieve 83% performance relative to human-based redactions in many challenging scenarios. For more information, please visit our poster. Thank you.
This ends our session. Let's thank again all the speakers.